Well, so in the last lecture we have developed theoretical concepts or basically definitions for this to understand thermodynamics and other chapters. Let's continue. Some of definitions are still left. So see, in thermodynamics, it is very important to understand what is a path, right? And whenever more than one variables are changing in any process, right? So every time you have to design the path, and if you are not able to design the path, it is difficult to solve the problem. Suppose that energy, I am taking just example, suppose that energy depends on temperature, and suppose that number of moles, right? So there are two variables on which suppose that energy depends. So and if you want to change, if you want to calculate the complete change in energy, then what you have to do, first you consider moles is constant, then calculate the change in energy due to the change in temperature. That is one path. That is one path. And now you have to make the temperature constant and then calculate the energy change due to the number of moles. So accordingly you can evaluate the total change in energy. So this path is very important. So path is what? Path is basically how this is defined in thermodynamics. Path is basically sequence of intermediate states. Path is the sequence of intermediate states. Intermediate states, right? See, suppose that this is initial and final state. This is the initial state, this is the final state. So in between these two states there are many, you can say, intermediate states we can design here in between, and that intermediate states is called what? Path, right? For example, if you see, suppose that I am taking here pressure and here temperature in Kelvin and pressure in bar, right? So suppose that these are the right. So this is one state. We can say this is initial state and this is final state. So in between these two states, there are so many. There are so many intermediate states are possible. So if we join all those intermediate states, right? Intermediate states. So this will construct a path, right? This will construct a path. So path is basically the sequence of intermediate states, right? This is a initial. This is an initial state. This is a final state. We have so many states here. So if we do here, if we do the infinite, put a infinite path, means if we proceed this process through very slow steps, very small steps, very small steps, if we put intermediate states, then the process is called what? Reversible. And if we do the fast, then the process is called irreversible. And this is very relevant and very important points to calculate the thermodynamic parameters in reversible and irreversible process, right? So slowly I will shift, I will cover that. So hopefully all of you are clear what is the path. Path is the sequence of intermediate states. So this is called path. So this represents a path of a process. Path of a process. So next discussion, my discussion is based on this process. What is a process? So process basically describes the path, right? Process describes the path. So this is very close definitions. All these are. So process, this describes the path, right? So any thermodynamic process or process here that describes the path of change of state. So describe the path of change of state. Change of state. So this is initial state, this is final state. So what do you mean by initial state? Here some value of P, V, N and T is there, and here some value of P, suppose that this is P dash, T dash, N and P, right? So these are the states. If you want, you can miss V from here because 3 variables are sufficient. And if you want, you can write all the 4 because all 4 are there, right? Always there. So describe the path of change of state. So in this, connection, one very important point is reversible process. Reversible process. So don't be confused with the chemical reversibility, like if you are writing A gives B, right? A gives B and B gives A. So this reaction, you can say this is a reversible reaction. So don't be confused with such type of definition here, because this is a thermodynamic reversible process and it has some different meaning than this, right? So don't be confused with the chemical reversibility. Don't stick on the chemical reversibility. Okay, chemical reversibility is the part of thermodynamic process, thermodynamic equilibrium. But here, this reversible process had some different meaning, right? So a reversible process, I am writing here some of the feature of reversible process. And if you, collectively identify those features in any process which is used to describe any path, then you can say the process is reversible. So first feature of this reversible process is that it is relatively very slow. Relatively very slow, right? So compared to other irreversible processes. Here our reference is the irreversible process. See, two main processes we have, reversible and irreversible. So relatively very slow compared to the irreversible. So irreversible processes are relatively fast. Okay. Second point is system itself and system with surrounding is always in equilibrium at every point of change, right? So system itself and system with surrounding are always in equilibrium at every intermediate state. Every intermediate state, right? So when you initiate any process, it has definitely initial states and it has some final states. So between initial and final state, there are many intermediate states. So at every intermediate state, system and surrounding are always in equilibrium, and system itself also in equilibrium, right? So see, what is the meaning of system itself in equilibrium, and right from beginning we are talking about this equilibrium, right? So system itself equilibrium means, suppose that if you have taken a system like this, a gas you have taken, so throughout the system pressure should be constant, throughout the system temperature should be constant, right? So if T and P are constant throughout the system, generally we, will not take V and N to define this, but they will automatically, they will constant, and in the whole system it is homogeneous. So if this T and P in the whole system is constant, then you can say that our system, suppose that pressure P is here, so here in the bottom also P, right? So means P is constant with respect to time, T is constant with respect to time, each and every point of the system. So this is the meaning of system itself in equilibrium, right? That there is no two different pressure zone in the same system. There is no two or more temperature zone in the same system. If in the same system, within system, two temperature zone, then you cannot say that our system is itself in equilibrium, right? And this system is equilibrium with the surrounding. Suppose that I have taken this piston is movable, and massless and frictionless piston if I have assumed here. So what will the meaning, what is the meaning of system with surrounding? So here in the different region of this our system pressure is same, means pressure itself in the equilibrium, mechanical equilibrium. And now if the pressure of gas is equal to the P external, so you can say that your system is in equilibrium, is in system is in mechanical equilibrium, mechanical equilibrium with surroundings, right? And temperature of the system, T of surrounding, T of system, P external. So T of system is equal to T of surrounding, then the system is in thermal equilibrium equilibrium with surrounding, right? So basically these two variables, because these two are potentials and they have ability to do something, so these two are considered to explain this equilibrium. Although when these two are constant, v is also be constant in that moment, and number of moles are always constant. So this is the meaning of system itself in equilibrium, and system with surrounding is in equilibrium. Suppose that this piston is slowly shifted upward. So at every instant of initial and final state, every instant, every intermediate state, the system is in equilibrium with the surrounding. So how is it possible? How is it possible that when system is in equilibrium with the surrounding, there should be no movement of process? There is, but we can arrange this type of system. Remember, reversible processes are ideal processes. So such type of process will not exist in the nature. These are not the natural processes. So, but we can do the arrangement. See here, I have written here, but very carefully. I have written here P external. I have not written here P atmospheric. P external means, suppose that if we put some mass here on the piston like that, then the pressure of external is equal to P external is equal to P atmospheric plus pressure due to this mass, pressure due to mass, right? Or pressure equivalent to the mass. So now the gas will hold this piston at this initial state. So pressure of gas and P external is equal. And suppose that if we remove one particle from here, then piston slightly shift and achieve another state. Then if we remove another particle, then this piston will move upward and attains the another intermediate state. So this is the meaning here. That's why I have not written P atmospheric, right? P external. So, and the main point I have written here in the first point, very slow. It means the here suppose that this process we are studying this expansion of this gas. So it means in this process the driving force, some driving force is there which drives this piston upward, and some opposing force is there. So driving and opposing forces are balanced, almost. We cannot say equal, but they are almost balanced. So what we can say, P gas, suppose that we study this expansion. So P gas is equal to, we can write P external plus minus dP, and dP tends to 0. So this will demonstrate a reversible process for expansion of gas. For expansion of gas, right? So for expansion of gas, this condition exists. So you know, always in equilibrium, such type of equilibrium in which every intermediate state we are getting a new equilibrium. So such type of equilibrium are known as quasi-static equilibrium. So we can say, third point, it is basically the generalization of second point. So we can say that system with surrounding always in quasi-static equilibrium. Quasi-static equilibrium, right? So this is the, important feature of this reversible process. Hopefully, all of you are understanding this reversible process. Also, you can say ideal process. Ideal process, right? One more feature is this, and usually, I'm always convinced with this, and this is very important feature. And I used to use this feature only to explain, but it requires, understanding, a better understanding of the subject. That reversible process can be reversed by same path, can be reversed by same path. Means between initial and final state, when you have different intermediate states. So from any one point, suppose that if we take a PV plot, if we take pressure volume plot, and suppose that we are studying the expansion, and N and T are constant. So all of you are knowing this is isotherm, and you will get this path, this type of path. Isotherms, Boyle's law, all of you are clear. This is initial state, this is final state, or we can write this is state A, and this is state B, this is initial, and this is final, right? So if you move from A to B, suppose that you are moving from A to B along this path, so you can reverse, if you can reverse with the same path from B to A, following the same intermediate states, then the process is reversible. And if you cannot, reverse from the following the same path, then your process is what? Irreversible. Then your process is irreversible. So these are the features which you can use to understand reversible process. Reversible process are relatively slow, very slow. In this system and surrounding and system itself, always in equilibrium at every intermediate state. Don't think that equilibrium means that is the final state. Between initial and final state, we have infinite equilibrium states. We may have infinite equilibrium states. Suppose that if you have taken a pressure, gas in this system, and you have put it some sand particles here, and system is in equilibrium, means P gas and P external is equal. Now keep on removing one part. Suppose that you have removed one particle of sand from here. What will you observe? You observe nothing. But you can feel that, okay, if I have removed one particle of sand, then piston slightly shift upward. You can feel. So if the process is so slow, then you can achieve this reversible process, right? So keep on removing each and one by one sand particles. So finally, after some time, we will observe, okay, piston slightly shifted. Now visible difference you are getting. So if the process is so slow, then you can achieve this reversible process. So if any process is proceed in such a slow manner, then the process is called ideal and your calculations are valid, your equations are exactly valid what you have developed. And in future calculations many times we are assuming that our system or process is reversible, means our system is moving from initial state to final state through reversible process, and for that we are developing the formula. All of you are knowing that first we develop the formula for idealized process, then we do some correction and some addition modification in that formula for the real processes, right? So most of the formula you will get here for reversible process, right? Okay. So hopefully it is very much clear to all of you that what is the meaning of reversible process. And I found this is the fantastic definition of property of this reversible process. This will tell everything, right? Means if a process is reversed by saying, then this is reversible, right? So, can you tell me any natural process is reversible or irreversible? Natural process. Natural process. See, natural processes are irreversible. Natural processes are irreversible, not reversible. Hmm. If natural processes are reversible, then everything is under equilibrium, static equilibrium. Quasi-static equilibrium means very slow movement will take place. Suppose that rainfall, if it is reversible, then what will happen? Rainfall means condensation and evaporation, very slight difference in their rates. Then what will happen? It will appear, means droplets starts moving from cloud, and it will reach on the earth after 1 year. Hmm? It is so slow process. So this is all natural processes are reversible. Our growth, plant animal growth, that is also irreversible. There is no mean that if you want to become 5 year old, hmm, by your present state, you cannot you cannot be a 5 year old by reducing yourself in that direction. You cannot. So all natural processes are irreversible, right? Now see what are irreversible process. Irreversible irreversible process. So if you want to define irreversible process, so see, first feature of irreversible process, relatively fast. And second feature, system and surrounding in equilibrium in the initial state and in the final state. System with surrounding, system with surrounding surrounding is in equilibrium is in equilibrium in initial and final state. Final state. There is no concept of intermediate state here. There is no concept of intermediate state, right? But if the system is not in equilibrium, you cannot measure any macroscopic properties and you cannot observe this TP, right? So system should be equilibrium, otherwise this is the violation of thermodynamics. And third important feature is cannot be reversed by same path. Same path means you cannot reverse such type of processes by same path. So means driving and opposing forces are greatly differs. But under final state, your system is in equilibrium, right? Suppose that I am taking the same case. P and V. Suppose that this is initial state and this is our final state. Then what will happen? So this so this is what path designing, what I have told you in the beginning, that when two variables are changing, so what you have to do, you have to first design the path by keeping one variable constant, then by keeping other one is constant. So see, this is our initial state A, this is our final state B. So from A to B, first we have moved from here to here. I have taken one I mean intermediate state here in this right process. So one intermediate state here, and after that at this time volume is constant, this is volume constant, and pressure is changing, and now pressure is constant, volume is changing. So this is the irreversible path. So irreversible paths are looks like this, right? It may be this also, no problem. Okay, it may be like this also, but I have shown you one path and simple path, and in most of the cases you will find this type of path. But I am not restricting you that only this path is possible between this A and B. Any path, any type of path is possible. But this is one of the that those paths, right? So this is the expansion because volume is changing here. Volume is, initial state is this. See, this is initial state and this is final state. So volume here is less and here volume is more. So expansion is taking place. And if you want to move irreversibly from here to here, you cannot move like this. Now you have restrictions, right? And if you have moved like this, then the process is not irreversible. So one of the possible and most appropriate path of reversible reversing this is like this, right? So this is the path. Again I am telling that this is not the only path to reverse this, but this is one of the best and well understandable path for you, right? So this type of process if shown to you, so this is irreversible process. irreversible. Means you cannot reverse the irreversible process by exactly same path. Okay, clear. And if you compare here intermediate states in reversible process, you have infinite intermediate states, infinite, very large. And in irreversible process, the intermediate states are less. You can put one more point here, that irreversible process have less or very less intermediate states, you can say. Intermediate states. We cannot say that there is no intermediate states, but compared to the reversible, we have less intermediate states, and but they are infinite. You have to add. So these are the features of irreversible process, right? Clear? And they are real process, real and natural. All natural processes are irreversible, right? So natural processes are irreversible and have this feature. Through this you can recognize, right? You can recognize. So this is about reversible and irreversible process. Hopefully all of you are clear, right? Well, see some other processes. These two are the main process, reversible and irreversible, right? And now some other processes like first I am taking isothermal process. Isothermal process. So isothermal process means change in the variable at constant temperature, right? So you can write for isothermal process delta T is equal to 0, right? So delta T is equal to 0. You can write for any isothermal process, and isothermal process may be reversible, may be irreversible, right? Isothermal process may be reversible, may be reversible, reversible or irreversible. Reversible, right? So isothermal process may be reversible or irreversible, and delta T is equal to 0 means temperature is constant, means constant temperature. So what is difference in this reversible and irreversible? It is very slow, very slow, and it is relatively fast. Means if you achieve initial and final state, even the same initial and final state you can achieve, right? From this reversible and irreversible. So if you do slowly, changes are very slow, then this is reversible, and if the process is relatively fast, so it is irreversible, right? Now see, you can represent this on PV plot as well. How to represent isothermal process? So I have already shown you this, but again, this I am showing you. So this is the isothermal plot for any process, and see this. This is the initial point number 1, and this is the final point. Let it be. It is the final point. This is V1 and this is V2. From here to here we are moving. So which type of process is this? Expansion or compression? This is expansion. Expansion, because volume is increasing. Why this is expansion? Because V2 is more than V1. V2 is more than V1. So this is expansion. Okay. And you know, T is constant. So T is constant. And you know, when the process is very slow, then this type of shape you will get. So this is basically, you can say, this is basically isothermal and reversible path, right? This is isothermal reversible path. Reversible. And if you do the, irreversible, then the path is different, right? Irreversible path is different for this. I am not drawing here irreversible path. I am drawing here only reversible path, right? So when in future it will come, then I will draw, I will show you. But I have already shown you. See, this is irreversible, right? And isothermal as well. See here, from here to here, temperature is constant, right? So this you can consider as a irreversible isothermal plot. But one by one I will explain. So this is isothermal reversible expansion of gas. Expansion of gas, right? So, and particularly ideal gas, not for real gas. So this type of plot you will get. So isothermal process, hopefully all of you are clear that temperature is constant. It may be reversible or irreversible. And this is, I have shown here, reversible isothermal expansion of ideal gas or gas, right? Now come to the next, that is isobaric. Isobaric process. Isothermal, second is isobaric. Isobaric. Isobaric process means P constant, P constant, that is delta P is equal to 0. It may be reversible or irreversible. But I am putting here a star because this is irreversible. Isobaric process is a paradox, right? Means a lot of debate you can get for this, that there is no isobaric irreversible process like that you may find anywhere. Everywhere you can find this, right? So what I am trying to say, that in isobaric process, reversible path are very easily you can demonstrate, you can identify. Irreversible path, it is a little bit different. And if I say that okay, the path is almost same for reversible and irreversible, reversible isobaric, then it is not I mean incorrect, right? So this is that's why I have put it here star. This is a paradox basically. Hmm? That irreversible isobaric process, because we don't have any other path like here in reversible isothermal process. Reversible and irreversible, they are clearly distinguished, right? See, this is irreversible isothermal path. So this is this path and this path both were clearly distinct. But here in case of isobaric, probably we do not have a separate path for irreversible and reversible. That's why sometimes people say that okay, there is no such process, right? But I'm not agree with that. Isobaric irreversible process may be there. The only difference is that this is very slow process and this is relatively fast process. Okay, I am this convinced that okay, we don't have different path. We don't have different path for irreversible and reversible. The connecting intermediate states are almost same. What we are getting in both the cases, so that the path is same. But I cannot say that okay, both are same. No, 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 no. That irreversible isobaric process is not feasible. Some people they say okay, there is no such irreversible isobaric process. But remember, both the processes are there. The only point is that we cannot distinguish the path of reversible and irreversible. Means we can say that intermediate states are same in both the cases, right? So don't try much about this, leave that. So how to represent this on the PV plot, you can very easily put this on the PV plot. Suppose that this is P and this is V. So okay, suppose that this is at temperature T2 and this is at temperature T1. So this is what? Isotherm. Isotherm. This is another isotherm. These are two different isotherms. Now we can put a state here. This is V1 and this is P1, right? So this is P1, V1, and along this line temperature is T1. So this is one of the state, N is constant. So P, V, T, all the values are known at this point, so and constant, so this is I state. And now if your process is moving like this from here to here, this is another state, right? So here V2, volume is V2, pressure is P1 and temperature is T2. T2, V2, P1. And here this is P1, V1, T1, right? So this path which I have shown here, this path, this line, from here to here, this is number 1 and this is number 2. So from 1 to 2, 1 to 2 is called isobar, isobar, right? So this is isobar, and here T2 is greater than what? T1. T2 is greater than T1, right? So here we can say this is what? Isobar, and this is reversible. And if you do in the one step, then this is reversible, and if you do the in many steps, infinite steps, then this is what? Reversible. And if you do in the one step or two step, then it is irreversible, right? But more or less the path is same for both here in the isobaric process, right? So hopefully this is clear to all of you. Isobaric process, reversible and irreversible have almost same path, right? And meaning is clear that the pressure is constant. So this is isobaric process, right? So I'm trying to show as much as possible the variables and state on the graph, right? Now the third one is adiabatic process. Adiabatic process, these are very important. Adiabatic process. So see, in adiabatic process, there is no heat change, no heat change between system and surroundings. That is, you can write delta Q is equal to 0, right? There is no heat change. How it is possible? It is possible only when your wall of the container is made up of wall of your container is made up of some adiabatic material. So if this wall is made up of adiabatic material, means material which does not allow to pass the heat, adiabatic matter, right? So if this is made up of perfectly thermally insulated material, means this will not allow the heat to go out. So if any process is processing inside this, then that is called adiabatic process. It is also, it may be reversible and irreversible, both possible, right? So adiabatic process may be reversible or irreversible. Both have distinct path. You cannot say that both have same path, right? So both have different path, not like this adiabatic isobaric process. So and when I will discuss detail in the adiabatic process in detail, then I will let you know that how this reversible and irreversible processes are in the adiabatic. This is just definition and introduction, right? So how to represent this adiabates, right? So see again, I will try to take the similar plot, PV plot. So on PV plot you can express all these processes. This is P, this is V. So so this is suppose that here state 1 is there. So so this is second, this is T1 and this is T2. T1 is greater than T2, right? So this is these are the isotherms, and this line represents adiabate, adiabate, right? So this is adiabate. These are isotherms. This is initial state. This is final state, right? And V1 and here V2 and here P1 and sorry P, this is P1 and this is P2, right? So what is the difference between this isotherm and adiabatic? Both have almost same shape. See, if you see here, this isotherm and adiabatic both have same shape. The shape of the path is same, but remember there is a difference in the slope, right? There is a difference in the slope. Okay, so this is adiabatic reversible, right? Adiabatic reversible path. So isotherm and adiabates, they differs in the slope. Shape is almost same type of path you will get, but both have different slope, right? So I'm not showing here this irreversible process. I have shown here only reversible process. So when I will discuss this adiabatic process, because I will discuss each and every process in detail, so at that time I will clearly distinguish these two processes, reversible and irreversible, and I will show it on the graph as well, right? So this is adiabatic process in which there is no heat change between system and surrounding. Reversible, it may be reversible and irreversible, and the representation of this is this. And isotherm and adiabate both differs with respect to the slope. So I am putting here this point so that you can remember. Isotherm isotherm and adiabate. Adiabate, this is called adiabate, this is isotherm, right? Adiabate differs with respect to slope, right? So this is adiabatic process. Similarly, fourth one, isochoric process. Isochoric process. Volume constant, delta V is equal to 0, right? And this also may be reversible and irreversible, right? T1, T2. So this is state 1, this is state 2, P1, P2, right? So this is isochoric process. It may be reversible and irreversible. Again, the same condition with isobaric, that path is almost same. So again, here I am putting one star here also on the irreversible. So this is see, T2 is greater than T1 here. T2 is greater than T1. Here you have P2, T2, and this is V, P2, T2, V, and here P1, T1, and V. So this is another state, this is initial state, this is final state, and this is isochoric path. This is isotherms, these are isotherms, isotherms, and this is isochore, 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 right? So this is isochoric process from here to here. This is isochoric process, right? So next one is, so some other processes are also known like cyclic process. So if you start from some initial state and you will get back to the same state, then that is a cyclic process, right? So we will see when I will discuss different processes in detail. Then the cyclic process also I will discuss in one case. So these are the main processes which all of you should what understand, right? And try to understand the drawing, plot, how to represent on the different processes on the PV plot, right? So see, right from beginning, I have shown you all the different processes: isothermal process on the PV plot, isobaric process on the PV plot, adiabatic process on the PV plot, and isochoric process also on the PV plot. Because this is most important relation, and from this we can explain each and every thermodynamic process through this PV plot. That's why this is preferred. Not that we cannot plot between P and T or B and T. Whatever you can plot. But I have considered PV plot because on this we can explain all these processes, right?